Okay, people, we're ready to get started. It's a real pleasure to have Bob Copier speak with us today. You remember I told you before that there's a group that has looked at, we talked a lot about how you price climate damages and that sort of thing. And you remember the discounting and ranges and all that stuff, and nobody faked. And there is also a completely empirical way to sort of do this. And so Bob has been at the forefront of that effort since its inception. I guess the three principals are Michael Greenstone, who was in the Obama White House. He was head of the Council of Advisors.
I can tell stories too, but yeah.
And then Solomon Shang, who wrote the paper and then Barney was here. He was educated at Chicago and Caltech. And so was a geoscientist, historically working mostly on sea level rise, I think.
For the last decade, yeah.
But also had a number of significant stints in the policy sphere. And you see this more and more now, where people who were trained as scientists spend time in Washington under various kinds of programs at universities doing significant policy work. That migration appears to be a little easier than the reverse migration. That is, the policy person who then gets subsequent training in science. That's not impossible, but the learning curve appears to be longer just because there's a lot of sort of background material that you also need. So in any case, he's an interesting, if anybody is a scientist who feels drawn to and compelled to do policy early in career, he'd be a good person to talk to. So without further ado, Bob, why don't you take over?
Sure. Thanks, Steve. So I'm going to talk to you about a couple of different things, but I think we can fit them together under the category of understanding and managing the risks of climate change. But to do this, I don't know whether you guys have talked about conceptions of risk as opposed to other conceptions, damages, or whatnot, so forth. So let me just give you a little bit of background on what I mean by risk. So this is a figure from the Intergovernmental Panel of Climate Change with their definition of risk, which is at this intersection here in the center. So risk is defined as the intersection of three things. Hazards, meaning something physical that has the potential to create a risk, say high water levels. Exposure, meaning that there are things that people care about. That could be people, it could be buildings, it could be ecosystems that are in harm's way. And vulnerability that relates sort of the magnitude of the exposure and the hazard to the actual damage, to the effects on people. And so the intersection of these three things is what we talk about when we talk about risk. In the climate context, in the IPCC's ways of thinking about this, the hazards are basically driven by climate. So they can arise from natural variability. So we have a particularly strong nor'easter or hurricane this year that might have happened in a similar form regardless of climate change, and to human influences on these hazards. The vulnerability and exposure are products of socioeconomic processes. So how wealthy people are, what sort of climates they're accustomed to, what sort of investments they've made to affect their adaptation, and also governance. And these things are not independent. It sounds like you've talked about DICE, so you can think about how this schematically relates to the little world of DICE, but the socioeconomic processes give rise to emissions and land use changes, which drive anthropogenic changes. And then the impacts come out of risk, but then affect both the climate and socioeconomic processes. So this is one sort of very natural science, in many ways, driven way of thinking about this problem. And I want to note governance hanging out here in the corner there. Because another way of thinking about this problem, and sort of inverts that, right? So if we think about the idea of risk governance, This is a conception that applies in the climate area, but is also, you can think of many other risks: terrorism risk, nuclear waste risk, can think of anything that is a potential harm to you, right? And in risk governance, we sort of think about this as a iterative process going between risk assessment, which is essentially the world of the IPCC thinking here, and risk management. And I'm sorry, these are a little blurry the way they've projected. They're not on my screen. But we can think about this as a cycle with a lot of communications in it, right? So we might identify a potential risk. There's a potential risk of democracy collapsing in the United States. Some sort of risk appraisal that leads to some sort of of judgment about tolerability of acceptance. So discounting, in what you've already talked about, is part of this question of, well, how much do we value different risks? And then this feeds into whatever sort of system we have for managing the risk. Can be some combination of regulatory and other sorts of management that then sort of iterates back and forth, with risk communication being a key part of this. So for most of this lecture and the sort of work that we do in the Climate Impact Lab, we're focused on sort of the quantitative risk assessment, so figuring out what the risks are. But I'm going to talk about risk management a bit at the end as well, in the context of, well, for coastal climate risk in particular, where I think some of these things are better thought out, how do we deal with this information that we've discovered about risks? So Steve already plugged the Climate Impact Lab. Again, I apologize that all of this is blurry on your screen and not on mine. But we really are not as pixelated as we look. These are the 4 principles. So Steve left out Trevor Hauser at the Rhodium Group. And one of the things that's important about the partnership is this is a partnership of 3 academic organizations and a private sector consulting firm. And the private sector work...
They can change the display setting if you want the rest of your slides to be clear, or you can
well, I think having them might be clear might be nice. So let me talk, you work on that. I'll talk about the Climate Impact Lab. So we started as a partnership. Really, our deep history goes back to 2013, and it goes back to Princeton. Because Saul Shung, who is at Berkeley as a professor there of economics, was at the time a postdoc here with Michael Oppenheimer. I had been a postdoc here 2007 to 2009, and Michael thought the two of us should get together. And out of that work evolved a project called the Risky Business Project, which was funded by Michael Bloomberg and Tom Steyer and Hank Paulson, and led in a book that came out in 2015 on the economic risks of climate change in the United States. And out of that, it's still the same, but is it? Okay. Out of that, we built this collaboration, the Climate Impact Lab. So Trevor at Rhodium Group, Michael Greenstone at Chicago, Saul Shung now at Berkeley, and me. And now we have about 30 people working on this large team. And our fundamental goals, there we go, I'm going to say Princeton connection. Our fundamental goals are 3 things, right? We're trying to use the available data about how people have responded in different places with different climatic experiences to weather and climate variability in the past, and use that to understand what the potential risks are they face going forward, with the aim of, 1, sort of being an information function, raising awareness about climate change and its impacts, 2, influencing policy. So I gather you've talked about the social cost of carbon a little bit, right? So one of the key things we're trying to do, and both Michael Greenstone and I were involved in 2009 and 2010 in the US government's first social cost of carbon analyses. We're trying to put the damage function there on this sort of empirical basis. And 3, while the social cost of carbon is very interesting and important, particularly in the context of US benefit cost regulatory analysis, I'm not sure I personally would be that excited about this if that were the only reason to do it. But in order to do this well, you don't just need to know sort of what is the global scale damage from climate change. You need to know what's happening at a local level or what the risks are at a local level. And that is critical information for both communicating with people and helping them start to think about what sort of actions need to be taken to deal with these potential risks. So you've probably talked about RCPs before, but I thought I should show this up here because it's sort of hard to talk about projections of climate if we don't start with this basis. But these are the sort of standard emission scenarios that have been used by the climate modeling community for the last decade or so. There's now a new generation of emission scenarios that are a little bit different, but our work so far is key to these. And so this figure here is showing you 3 of these RCPs, which I'm just going to call high, medium, and low emissions. But if you remember the jargon, this is RCP 8.5, this is RCP 4.5, and this is RCP 2.6. And these are global carbon dioxide emissions under each of these RCPs. So here's the historical emissions. We're currently at 42 billion tons. RCP 8.5 sort of has like the fastest rate of growth we saw over this time period, 1990s and 2000s, continuing unchecked, leading to a doubling of emissions by the middle of the century. RCP 4.5 starts out a little bit lower than we are today, but essentially has this sort of flat plateau that we saw for a few years that now seems to have broken, continuing to the middle of the century, and then a decline. And then RCP 2.6 leads to net zero global greenhouse gas emissions in the last quarter of this century. And if we look at sort of global mean temperature projections, roughly we can think about the RCP 8.5 is 4 to 5 degrees Celsius above pre-industrial. RCP 4.5 has about 2 to 3 degrees, and RCP 2.6 has a 1.5 to 2 degree scenario. So, as I'm sure has already been emphasized, this very ambitious project, this is the one that all the nations of the world have set out as their formal target in the Paris Agreement. If you look at the commitments people have made so far, the nations have made so far, it gets you a little bit above RCP 4.5, so more like a 3 degree world. So I was told we wanted to do a clicker question. Here's my clicker question, and this is sort of just there's no right answer here. I want to get your sense of optimism or pessimism about the future of the climate. And so let's just take these sort of given this on the right, this is sort of RCP 2.6, this is RCP 4.5, and this is RCP 8.5, and C is in between. People respond very quickly. How many people are we looking for?
Just give them, at some point, give them 5 seconds.
Okay.
Like now.
All right, 5 seconds. All right, so did I erase? Yeah, there we go. So people are moderately optimistic, I think. That's good. I feel 13% think we will get on 1.5 to 2 degrees. And I don't know what the people hitting E thought, but okay, that's good to know. How do I make that disappear? There we go. So our work in the Impact Lab, as I said, is sort of focused on essentially using big data or statistical approaches. So the general idea is to compile available data about historical damages and learn from that data set about these relationships between about hazard and exposure and vulnerability. So there's a few sectors that we have ongoing projects on right now. I'm going to talk about work related to 2 of them. Sectors in which the impact categories in which these sorts of approaches might apply might be looking at how people die or don't die as a response to climate change, looking at effects of climate change on agriculture and crop yields, looking at effects on energy demand, on labor, which is an interesting one and one that's probably a very important role in the overall economy because labor is an important input into the overall economy, but not something that there's been as much work on. But if you just think about it like in a hot day, people can't work as effectively inside, or especially if they're outside. Civil conflict, there is some empirical work on the relationship between weather extremes and civil conflict. Civil war, it's pretty controversial, but most people agree that there is a relationship, and there's a question as whether there's a direct relationship or if it's intermediated by something else. There is a remarkable thing, and this was the one that was most surprised to me when I started in this area 6 years ago, a quite strong relationship between crime statistics, particularly violent crime, and weather exposure, migration, and coastal. So I'm going to talk, since we don't have a lot of time, a little bit about mortality, which will give you the flavor of the sort of the impact lab approach to doing these things. And then I'm going to talk about coastal from a somewhat broader perspective than just the impact lab, because that's where I'm going to be able to start to talk about things like risk management that I want to bring up as well. So here's this is work from a paper led by Tamara Carlton, who was a grad student at Berkeley, is now a postdoc at Chicago, will be starting at Santa Barbara as a faculty member next year. And here's the sort of basic approach. So one, if we're going to use big data approaches, we need to get big data. So the first step is essentially collecting and cleaning a whole lot of data. So this is showing you the mortality statistics that we were able to acquire. So blue are the areas covered. Then down here is our timeline. So for India, there's data that goes back to the 50s. For the US, it's in the late 60s, and so forth. And we think that, in the courses of doing this, we've built the most comprehensive, self-consistent set of mortality statistics that exists. And the reason why we built it is because we then want to take these and compare the data on mortality to weather data. So figure out, okay, the person in Princeton, New Jersey, in a year with a high mortality rate versus a low mortality rate, how does the mortality compare how does that relate to temperature? So I'm going to gloss over all of the math. If people are interested, we can go through it later. But this is sort of the outcome of that sort of analysis, right? So we're trying to learn the statistical relationship between exposure to days of different temperatures. So this is the temperature of a single day, so from -5 to 35 degrees Celsius in each of these blocks, and the effect on the mortality rate of exposure to that day. So this is in units of deaths per 100,000. And you basically look at the effects of all of the days in the year together, how they line up. And then we do one other thing, right, which is recognize how heat and cold and mortality relate in the United States is not the same way they relate in India, because people have different adaptive capacities, people have different experiences of climate, and so we have to learn about those differences from the data. But it's more than that. It's not just India versus the US. It's also the effect of a hot day in Houston is a lot less than the effect of a hot day in Seattle. Why? Because people in Houston get a lot more hot days. They've made investments in things like air conditioning. So they're more insulated from the hot days than somewhere like Seattle, where they have much less experience. And you can see this pretty dramatically if you think about some of the heat waves in Europe over the last couple decades. There were tens of thousands of deaths in France from the 2003 heat wave. That wasn't a more severe heat wave particularly than the 1995 heat wave in the US Midwest, which caused about 1,000 deaths. But the difference was that there's a bunch more air conditioning in the US Midwest than there was in France. So what we learn is shown here. So here, these are relationships between exposure to temperature of different days and mortality. And it's sorted by the coldest, middle temperature in the hottest counties in the world, and low, middle, and high income. And what you see is that as you move from cold to hot, the curve flattens, and as you move from low income to high income, the curve flattens. Right? So poor people are more vulnerable. Right? These curves are telling you the vulnerability part of that relationship, the risk relationship, and rich people and poor people are more vulnerable. Yeah. So probably it's a statistical artifact because there aren't a lot of hot, low-income there aren't a lot of cold low-income countries, and there's not a lot of hot places where you get days of -5 degrees Celsius. So it's sort of that is, I think, probably just statistical noise, right? One of the challenges of doing this sort of work is that you really have to probe the data and say, well, is this just noise because there's no data that allows the statistics to make a fit? Or is it, there's actually something counterintuitive there, right? You could come up, if that decline were robust to a whole bunch of different ways of treating the data, you would say, okay, well, maybe there's some sort of protective effect of cold days, and you'd have to figure out what the mechanism is here. In this case, there's just not a lot of days below freezing in hot places. And so that's not statistically interesting. So using this data, we can infer how sensitive populations are, how vulnerable they are to heat, even where we don't have the data here. I don't know why. No, so the mortality statistics are available in a few different age bands. So there's like the under fives, the 5 to 20 somethings, the sort of middle-aged adults, and then the elderly. And it's the elderly where there's the strongest signal. So that's why I'm showing that here. Most of the mortality from extreme temperature is driven by the death of old people. So this is sort of the map view of what I showed you previously. So this is how much people are harmed from exposure to 35 degrees Celsius today. Like so this is for current socioeconomic conditions. And right, I mean you can so red are places that are more vulnerable. The paler colors are places that are less vulnerable. So if you look at the U.S., you can see places like the Northwest, and to some extent some of the rest of the North is more vulnerable than places in the South, and that has to do primarily with experience, so things like in how people adapt through things like air conditioning. You see poor places that even though they're hot are more vulnerable. And then you also know just when you do this sort of approach, you get statistical artifacts, like Antarctica is a statistical artifact. There's not 35 degrees days in Antarctica, nor is there much of a population there. But not only can we then manage to fill in the gaps in this map for today, we can then go and take the same approach and say, okay, well, what if we allow climate and socioeconomics to evolve over time following, say, one of those RCP pathways? So if we project the possible paths the climate might take under RCP 8.5 or RCP 4.5, and we combine that with scenarios of future population and income, we can take the same approach and say, okay, how does this sensitivity to hot days vary over time? And how does the exposure, where the people are, vary over time? And so let's do that. So let's take the physical hazard projection from large-scale global climate projections. You have to do something called bias correction to deal with the fact that global climate models don't all have the same base climate state as the real world. And here I'm just showing you sort of a median projection for the historical average summer temperatures under historic conditions, so that I can then show you, how this projects forward under RCP 8.5 to the end of the century. And if this map looks like it was taken out of a website with a little button here, that's because you can access all of these maps and play around with them on the Impact Lab website, impactlab.org. But this is median projections for RCP 8.5, so roughly a 4 degrees C above pre-industrial world. I can flip back into them just so you can sort of absorb what that implies. Say New Jersey looking more like, the Florida, for instance. Some places being extraordinarily hot compared to the historical temperatures. So then we say, okay, so here's the hazard changing. We use a variety of different standard socioeconomic scenarios to look at where the people are and what their income is. And then we can use our empirically learned approach to estimate their changing vulnerability. And so here's what we get. So this is projections for that same temperature scenario I showed you the temperature for of the impacts of climate change in terms of mortality, so deaths per 100,000. for 2100 in a high emissions future. And so what you see is that hotter places, for more equatorial places have more severe mortality impacts, poorer places have more severe impacts, and that cold places actually see a reduction in mortality. Right? And so if you're making an argument about why you need to act on climate change to the Norwegians, it can't be an argument about the direct impacts on human health in Norway, at least based on temperature-related mortality. You have to think outside the little bubble of direct impacts and think more globally about how this sort of change and this sort of change in other impact categories affects the whole global economic system and the global geopolitical system. So we can look at that in a little more aggregated approach to see some interesting patterns. So over here on the right, so here are current death rates from cardiovascular disease, cancer, infectious diseases, and injury. And then here's our projection for that high emissions future, broken down by income category and by climate category. So hot places, moderate places, cold places, poor places, moderate income, high income. And then also adding in something else I didn't talk about because of time, but is also critically important, which is that, I mentioned this difference between, say, Seattle and Houston. Seattle has a lot less air conditioning. Well, in a hotter world, people in Seattle are going to buy more air conditioning, and they're going to take other measures like that will reduce their mortality, but also incur costs. Right? So one thing to keep in mind when we think about impacts is, yes, we can adapt to many of them, but adaptation itself is not free. And so here we've also estimated what those adaptation costs are based on a comparison of when people choose to buy air conditioning, but at a more aggregate level. And so the light-colored things are adaptation costs converted into units of deaths using an economic magic called the value of statistical life, which could be a lecture on its own. And you'll just, for the moment, just accept that there's a way of making lives and dollars commiserate that economists like, regardless of how other people feel about it. So what you see, the basic story here is that low-income places, people die. High-income places, people spend money on adaptation and might actually see a reduction in deaths. Hot places, people die and spend some money, but they're largely poor places. Cold places tend to be wealthier and have more money to spend on adaptation. The other point is that this is for the high emissions trajectory, if you get on that moderate emissions trajectory, so all of you people who are voting between 2 and 3 degrees Celsius, right, cuts these risks by about 80%. So there's substantial benefit even in moderate emissions reductions. All right, so I think I have about 15 to 20 minutes left. Okay, so I then want to back up and talk about coastal impacts. We have an ongoing project in the Impact Lab that is looking at exposure to wind and surge during hurricanes and using a similar approach to learn about storm impacts, but that's not the approach I'm going to take here because I want to use this to talk a little bit more about management of risk and how we deal with uncertainty. This is a photo of the Port of Newark looking towards New York City. And I put it here to illustrate the fact that coasts are really important to the global economy and to global society. A huge fraction of global economic activity passes through the coasts, and about 400 million people currently live within about 2 meters or 6 feet of the high tide line, which are areas potentially vulnerable to permanent flooding from sea level rise over the century. If we look at some of the cities that are most exposed to the effects of sea level rise, this sort of will give you a flavor of where people are, right? So we see a lot of East Asian and South Asian cities here. We also see places like Miami, New York and Newark, New Orleans, Boston, Tampa, St. Petersburg. So this is sort of a story that is very relevant to our own region. If we look, in fact, at climate impacts in New Jersey based on other work we've done, probably the effects of sea level rise and changes in coastal storms are the thing that most directly threatens our state. So what's the problem? Well, so global average sea level is currently rising at about 4 millimeters per year. That's close to an inch every 6 years. If we look at where that's coming from, it's probably familiar to many of you, but the largest chunk of that is coming from ice melting on land. 40% of that is coming from the expansion of the oceans as they warm, and then there's a slim fraction of that comes from things like pumping of groundwater and letting the water run off into the ocean. When we start looking at hazards and risks, though, just like we can't look at a single model like DICE that looks at the whole world as a whole region and say something that intelligible, we can't just look at sea level from a single global number and say something that intelligible, because sea level, like temperature, like rainfall, like all the climate variables, differs substantially from place to place. So, here in New Jersey, we're seeing sea level rise substantially faster than the global average. That mostly has to do with the fact that the land is sinking here as a result of both natural processes and groundwater withdrawal. We have, when we move ice around, the effects on the Earth's gravitational field that reshape where the water goes. And so that means we get less sea level rise when Greenland melts, because Greenland has been sort of pulling water towards it, and when it melts, it sort of lets the water slosh away from it, but more sea level rise than the global average when Antarctica melts. And there are changes in ocean circulation, so things like changes in the Gulf Stream that also have a significant effect on sea level rise. This is showing you historical sea level rise in New York, New Jersey, and in the global average. So this is the global average sea level rise from 1910 to 2015. The orange curve here is the New York curve. The green curve here is the New Jersey curve. And as you would also see if you were to look at a record of something like temperature, right, there's a clear trend. There's also a lot of ups and downs, right? So this is the natural variability in sea level. So global, the difference between New York and global average sea level rise is largely the result of natural sinking of the land. This additional bit is largely a result of groundwater withdrawal accelerating sinking of the land along the Jersey coast. And this sort of long-term trend translates into a change in hazard. So one hazard associated with sea level rise is high tide flooding. So this is an interesting one to think about because it's something people experience regularly, right? It's when you can't get to your car because the roads are flooded. This figure here is showing you the frequency of high tide flooding in Atlantic City over the last 100 years, using the same high water reference level. And so what we see is that high tide flooding that happened maybe one day a year on average in the 1950s, over the last decade has happened about 8 days a year on average, in some years 18 days a year. And that is a result of sort of natural variability in the tides, in natural weather, things like winds, superimposed on top of this high and quickly rising sea level. So what do we see looking forward? If I had more time, we could talk about sort of the details of how we do sea level rise projections. But for this discussion, I just want to give you a sense of the hazard so we can talk about how we might think about managing it. So by 2030, we're using very likely, and in this case, I don't know if you've come across IPCC probability jargon, but very likely I'm using to mean about 9 chances, and at least 9 chances in 10, 90% chance. By 2030, we're very likely looking at about 10 to 20 centimeters of sea level rise relative to the year 2000 in the global average. By 2050, roughly 1 foot, about 20 to 40 centimeters. And then beyond 2050, we start seeing an increasing effect of which emissions pathway we're on. And I should note that for sea level, the differences between those emissions pathways take more time to reveal themselves because we're dealing with a much larger system with much larger heat capacity. So if you think about temperature, right, you've basically got to heat up the thin layer of the Earth, the atmosphere, and the surface. To heat up, to cause sea level rise, that heat has to warm the oceans, it has to melt ice sheets, and that takes longer to penetrate. And to absorb, the oceans have higher heat capacity, in other words. So by the end of the century, under the high emissions pathway, we're very likely looking at about 2 to 4 feet of sea level rise in the global average based on this analysis, which is sort of consistent with what the IPCC did 6 years ago. By 2100, we're very likely looking at about 1 to 3 feet, and then that difference continues to grow larger as we push forward more in time. So I mentioned that the Climate Impact Lab work grew out of a book that Trevor and Saul and I worked on for Mike Bloomberg and Tom Steyer and Hank Paulson. This is that book up here. And in this project, we worked with a firm called RMS, which works with insurance companies, to sort of translate the sea level projections that I showed you into impacts on coastal storm damage. And so this is showing you the percentage increase in coastal storm damages by state. So this is not dollar value terms, right? It's sort of, some states already have larger baselines, and so a percentage increase is less. But here, right, you're seeing Delaware, New Jersey, and New York popping out as having the largest percentage increase in coastal storm damages through 2050. You can also see, Florida looks relatively low, but in terms of dollars, Florida is starting from a really high baseline, in excess of $10 billion a year on average, and so this is still a very large number, and it's the largest in terms of absolute damages. But this sea level rise alone leading to pretty substantial increases in damages in a lot of coastal states. By 2050, based on this analysis, assuming without adaptation, so right, not taking into account people might move away from the shore, or people might build dams in some places, not taking into account those measures, and assuming that property prices are what they are today, we're looking at about a $9 billion a year increase in average annual coastal storm damages. And that's just through 2050. This is through the area where the sea level rise projections are relatively well constrained. By 2100, under the set of sea level rise projections I showed you, we're looking at national damages of about $50 billion a year, which is comparable to the damages from Hurricane Sandy every year and a half. But as I hinted at, beyond 2050, it becomes increasingly more challenging to constrain ice sheet projections. And that's because the physics of how ice sheets and the oceans interact is complex, and the state of scientific understanding is rapidly evolving. So this is a photo from a colleague, Knut Christensen, in Greenland. It's showing you probably a 20 or 30 meter high cliff of ice, and collapsing. And I'm doing this to allude to a mechanism that people in the ice sheet community, scientists in the ice sheet community, have started studying in detail over the last few years, which is a potential ability of ice cliffs to collapse under their own weight. So here's the projections I showed you before. We worked with Rob DeCanto and David Pollard, who are ice sheet modelers, to incorporate a set of projections that incorporated this ice cliff gravitational collapse mechanism and a couple other modes of instability into projections of the future of the Antarctic ice sheet. And so I'm going to show you how incorporating this one physical mechanism, which really the community hadn't been focusing on until about 4 years ago, into sea level rise projections affects the numbers. So that's going to be the hollow one. So does not make very much difference in 2050. Under a low emissions pathway, does not make very much difference in 2100. 30 to 80 centimeters, 30 to 100 centimeters. Under a high emissions pathway, though, it makes a huge difference. 50 to 120 centimeters is what we said before. This is 90 to 240 centimeters. So raising the high end by a factor of 2, basically. So how do we reconcile these numbers, right? This is just one study. There's a lot of different ways of trying to look across studies. But one project that Michael Oppenheimer and I and a number of others tried to do to get at this involves something called structured expert judgment. So this is sort of a formal risk analysis method that does basically what it says. We're asking experts for their judgment, but it's not a survey. It's not one of your clicker polls. And the reason why it's not a clicker poll is that we are calibrating experts for how much weight we give them based on 2 things. So one is their ability to correctly answer questions about things that are knowable, so not what's going to happen in the future, but what's happening now. But 2, also calibrating it based on their ability to estimate how uncertain they are about those things. Because what you don't want to do is have somebody who is very precise answers, who thinks they know the answer very precisely. Maybe they actually do have quite a bit of knowledge, but are overconfident in how precise that knowledge is. Maybe they're off by 10%, but don't recognize it. You'd rather give more weight to somebody who recognizes, maybe they're off by 20%, but recognizes that there's more error in their method. So we're basically calibrating experts to estimate how good a job they do of estimating their uncertainty. And so using the results of that study, I'm going to add a third layer on. Again, not a huge change for low emissions, not a huge change for 2050. This group of experts, as of 2018, sort of gave us a 60 to 240 centimeter range. So basically similar at the low end to the IPCC 2013 number, similar at the high end to this unstable ice cliff study. So what all of this reflects is that we're talking about a hard problem, and it becomes harder if we're looking at a world with high emissions. So I'm trying to show you a few pictures of exposure. So here we're looking at Miami-Dade County. This is Miami Beach with 2 feet of sea level rise. Depending on what set of sea level rise projection, there's about a 1 in 4% chance that you'd get here by 2050. Under high emissions, there's a close to certainty you get there by 2100 or soon thereafter. Under low emissions, about a 50% chance, and that would encompass about 18,000 people and $7 billion of property. Here at 3 feet, by the end of the century, here we start to see differences among approaches. Maybe it's 40%, maybe it's 97%. Low emissions in the 10 to 20% range, 85,000 people, $22 billion of property. Here's 6 feet of sea level rise. Very small chance under a low emission scenario, about 1 in 500. But under high emissions, here's an area where we get into what we call deep uncertainty. That is, there are fundamental scientific questions we don't know the answer to. Current experts can't agree upon the answer to them. And yet they have a pretty large impact on the future of this region. Is it 1% chance we look like this, or is it 40% chance? And how do we make risk management decisions without knowing whether it's a 1 or 40% chance that 880,000 people are going to be, currently live in areas that will be below the high tide line? So that's a challenge, right? As we look out further with sea level, but also with other variables, we get into these increasingly deep uncertainties. I want to highlight 2 other risk factors, and then I'll get into the risk management question. And I say I'm almost out of time, so I just make two points quickly. So this is U.S. tropical cyclone costs. So from 1980 to 2004, the average cost in a typical year of dealing with hurricanes was about $6 billion. If we In 2005, we had Hurricane Katrina. In 2012, Hurricane Sandy. In 2017, we had 3 large hurricanes. That 1 year alone, Hurricane Katrina, basically increased the average expected loss from hurricanes in a typical year from $6 billion to $18 billion. So one bad year, the average was completely out of whack. Right? This is what happens when you have sort of a very high entail. A single big surprise can throw expectations out of whack. Right? You might have had a very well-managed national flood insurance program based on the expectation that there would be $6 billion a year of flood damages, and then suddenly you have your one of year happens and that turns out to be completely wrong, and you have, as we have now, a flood insurance program running massive financial debts. So what does that mean in practice? Well, people in California are seeing a similar phenomenon now with the increasingly frequent and large wildfires. Right? The private sector insurers are pulling out of these markets because the risk is no longer manageable using that sort of economic approach. Meanwhile, the political approaches, the government approaches to managing these risks are also becoming a little stickier and a little less manageable. Puerto Rico right? We have disaster aid, which used to be sort of automatic in the aftermath of a disaster, becoming harder and harder to get out of the federal government. Right? Eventually it comes out, but we're going to see more of these sorts of political and economic risk factors as these risks change. The ultimate expression of that, right? If you have too many shocks, right, you can have state collapse, and then you get large waves of migration. So, right, Syria was not a climate-driven disaster, but although the drought there may have been amplified by climate change, but we can look at the effects of the Syrian migration on global geopolitics to get a sense of what some of the other risk factors might happen as we start seeing these more and more frequent shocks. So let me leave you with a few thoughts. One is that the consequences of our decisions in terms of how we choose to build the built environment often last longer than we might think. This is the Marion Power Station in Jersey City, New Jersey, from the Electric Railway Journal of 1911. So this was built in the 1900s by Thomas Alva Edison and his contemporaries. This map comes from that same journal, and it's showing you the electric grid of New Jersey in 1911. There's the Marion Power Generating Station. The Marion Switching Station, not a generator anymore, but it's still a node on the electric grid, flooded in 2011 during Irene, flooded in 2012 during Sandy. And in fact, you can find 7 of the 14 switching stations that flooded in New Jersey during Hurricane Sandy on this map of the grid in 1911. Right? So that was a 100-year lifetime effect, plus lifetime effect of these decisions. So what do we do? Do we rebuild unchanged in the aftermath of disasters? We've seen some of this along the Jersey shore after Sandy. Do we modify our communities to accommodate occasional flooding, things like elevating houses? But remembering, this is not a private homeowner's decision alone. You could elevate your house, but if your infrastructure is not hardened, it doesn't do you that much good if you're in the middle of a disaster. Do we build hard protective infrastructure, like the berms for the proposed East Side Coastal Resiliency Project? But we also have to remember that nothing is perfect, as the people of New Orleans learned during Katrina, and you also need to plan for those occasions when hard protection fails. Oh, sorry. We can think about expanding natural infrastructure. We can think about relocation. But ultimately, these are complex discussions that require a lot of local deliberative processes, right? It requires that we don't come out of Princeton or Rutgers with a single master plan. Requires that we engage with the communities and learn what their values are and how their decision processes work. And so I'm going to skip over that for the sake of time and just leave you with a couple final thoughts. So first of all, I would argue that to do this well requires that all of us in this room who want to go on in this area, recognize that we have to learn how to listen and not just to speak, that we have to learn how to work together across disciplines, right? This is not just a sea level science problem. It's not just a coastal geomorphology problem. It's a social science problem. It's a policy problem. And so that's one of the things we've been trying to train graduate students at Rutgers for the last 4 years to do through our Coastal Climate Risk and Resilience program. So some of you, if this is of interest, I'd be happy to talk more. But however we choose to adapt, the starting point has to be climate change mitigation. There's a big difference between a high and low emissions pathway, particularly in terms of some of these deep uncertainties. So thanks.